Hello, my name is Jason Sonnenberg. I'm part of the Wolfram Alpha chemistry team. And I'd like to share with you today some of the efforts that we've been doing in chemical education. And as the talk is titled, The Chemical Education with Wolfram Technologies. As many of you may know, we have quite a few technologies from the Wolfram stack for chemical education. There are four that I'm going to talk about today, namely Wolfram Alpha, the Demonstrations project, Wolfram Language, and the Wolfram Alpha Notebook Edition. I will touch just briefly on some of the developments in chemistry in the Wolfram language, but you should stay tuned to the talk immediately following this by my colleague Jason Biggs. He will be explaining in more detail the latest developments in the Wolfram language, and so I'll focus on primarily on the other three over the next half hour. So what have we been doing? It's been a busy year for chemical education with Wolfram Tech, and I'd like to share some of the things that we've been putting out. So to get things started, we kicked the year off with a 4-part blog series, hopefully some of you saw, where we were talking about how to use the step-by-step solutions aspect of the Wolfram Alpha Pro package to solve chemical reaction problems, to do solutions, to work with structure and bonding, and quantum chemistry. And those 4 blogs are available here. If you're a reader of Medium, they're also being cross-posted over to the Teaching with Technology blog over there. So if you haven't seen them, those are rolling out. We've got 2 cross-posted there currently. But the information there, it walks both the students and the users through how to use the technology, what it looks like, and how to take traditional homework problems and reformulate them into something that you can feed to Wolfram Alpha. So if you are looking to get your students or your colleagues involved with our tech in their classroom or their learning space, you might point them to these blogs to get started to see what we can do in real time. So besides adding more information on how to use the technology and trying to build tutorials to get your students up to speed without having to waste learning space time to explain it, we've also been expanding our coverage. So this time last year, we had another graphic that looked very similar, and we've had quite a few developments since the last WTC. Most notably, we have 3 new content areas. So we've now expanded our coverage into the equilibrium, into the area of kinetics, and the general aspect of molecules. In the chemical conversions, which is a quite popular feature that we have, we've added molar aliquots, and we're hoping to expand the aliquot support that we have going forward over the next year. In equilibrium, we now can take for a chemical reaction, if it's balanceable, and not a fragmented chemical reaction, but if it's fully balanceable, then we can spit back the equilibrium constant and the reaction quotient. Those teaching high school or, high school or chemistry in the middle school curriculum probably won't be dealing with reaction quotients, but we have support for both of it so that it cuts across the entire curriculum, whether you're at the beginning stage or quite late, say maybe taking PChem at a college level. Likewise with kinetics, we can now build the rate of reaction and the rate of conversion. For the molecules, this sort of piggybacks on the molecule development in the Wolfram language. We now have support for atom count, electron count, and proton count. And lastly, in our quantum chemistry section, we've expanded our support for orbital diagrams, sometimes called Aufbau diagrams. And we've also got support for determining valence electrons from the electron configuration string. So let's go see an example of this and actually show some of the features. So I'm going to start with the equilibrium constant because that definitely appears in the high school curriculum. It may not appear much at all in the grade school or middle school curriculum, but it's a nice thing to start with, to try and show how we can support not only high school and middle school folks, but also well up into the college level as well. So here, the query, which is linkable here, is we start with lead chloride going to lead to cation and the chloride anion. And what we see is that our step-by-steps, we always in our first step, we restate the problem to make sure that the student understands what's going on. We introduce, in this case, the variable that we're dealing with, the equilibrium constant, so in this case are represented by K. Then all of our chemistry steps in the second step have some sort of plan. This mirrors much of the pedagogy in current textbooks. So we set up a framework for students so that they can not only see how to get through this current problem, but also to have a toolbox of frameworks to tackle general problems of this type when they encounter them again. We then start off by balancing the chemical equation. This is fully clickable on the live website, and you would get more details. I'm not going to show that here today. Step 4, then we go on, and here we assign stoichiometric numbers. Again, we are very cognizant of always introducing variables for the things that we are talking about, so that the students not only connect the name to the variable, but they get used to the notation that they might see in the chemical literature or in their textbooks. And so here we grab the balance coefficients from step 3, we tabulate them, and then we follow the instructions for determining the stoichiometric numbers. In step 5, then we go on and we assemble the activity expressions. Now, if you're in an introductory course, you would just learn that all solids have a term that's 1, or for aqueous species, it's just the concentration. But we have details to dig further so that we can support the folks that might be taking PChem or the introductory student that's curious as to why in the world is this just 1 if it wasn't covered in their particular textbook. We'll come back to looking at the details of this in just a moment. So we have that ability to dig deeper. And then in step 6, I'm quite proud to report that the equilibrium constant is the logic is smart enough to determine what sort of subscript should be on the K. If you're in the concentration basis, if you're in the pressure basis, if you are in this case a solubility product. We know this information based on the states of matter that are coming through and were passed to us. So when students are working with the tool, if they pass us more information, we actually do utilize that. Last, we put together the expression and return the answer. So as I said before, we've got support for the upper level or more curious students for what's going on with these activity expressions. And the idea here is that you can click there and get more details. So let's click on the lead chloride, which has a value of 1. And what the student would see is more details provided, and it talks about how to construct the activity expression. And here is completely rigorous to the PChem standards of what's going on. We walk the student through the gory details, introducing all of the appropriate symbology, and explain why it goes to 1 and why we're raising it to a particular power. Likewise, for the chloride ion, since it's aqueous, rather than being a solid, we have, again, a fully phase-dependent description of what's going on, and we walk through the full expression with all the gory details. Again, if the student is not interested in this or don't need to worry about it, they just simply don't click on it. But we have it there for support across the curriculum. Don't know why that's there. Okay. So what else have we been working on? Besides adding new content areas and new topics that we support, we've been enhancing the details that we already have. And let's go through that. So in chemical reactions, you may have noticed, this is already live on the website, our layout for chemical equations has now changed. We use a column format where the name and state of matter is underneath it. It gives a little better layout. We've changed some of the font colors and whatnot to make it clearer. In our dilution calculator, when we introduce the equation, we now have a step-by-step support for the full derivation of this expression. So many times students forget dilutions or get confused if they want to see where the equation came from to potentially learn that process themselves rather than just simply memorizing, they can now click and see full details on that. We hope to expand this sort of from first principles derivations in our calculators and elsewhere in the chemistry step-by-step support going forward. We also did a major overhaul of our solution preparation. So if you didn't know it, you can ask Alpha how to create particular solutions. So you can, if you want something based on the molarity equation, such as this, you can just ask for, if you want 0.8870 molar sodium chloride, we'll show you how to go figure it out and that you need to dissolve this much sodium chloride to a final volume of 1 liter. We also know how to prepare, say, if you wanted to prepare from scratch concentrated hydrogen fluoride. Of course, this would be a little bit much more tedious, but we can handle those sorts of queries and understand concentrated as an adjective for the molarity that's automatically converted. If we're doing solution preparation from a dilution, such as in this case, for decimolar acetic acid, the software already knows that acetic acid has a concentrated version that's available commercially, and we use that as a starting point to do a dilution to prepare the solution that's required. Likewise, you can also tell Alpha what aliquot to start with to then do the full dilution to get down to the desired concentration. So all that is live and available today. Since many of us in the chemical education community are now doing things remotely, I'd like to highlight some of the features that we have in the Wolfram Demonstrations to help build your remote laboratory experiences, or just for have more engagement with a particular topic. So the Wolfram Demonstrations projects is ever growing and has a rather large group of chemistry-related activities. The team at the Compute to Learn team over at the University of Michigan has been uploading quite a few of these, and that team has been growing. We have an example here from Lafayette College chemistry students under the supervision of Professor Hendrickson. They've been creating, these are student-driven, student-created activities, at least at Lafayette, that are then used to simulate activities and homework problems and laboratory activities. And as you can see, you can change the wavelength that you're doing the measurement at, and whether you're at lambda max or not, it changes the results, and you can change the concentration, and this uses simulated data, so one could easily build activities around this classic Beer's law experiment so that the student could interact with simulated data and interact with the experiment at home without having to come into the laboratory. And this is just one of many demonstrations that could be utilized in this way to either expand a homework problem or a series of classroom activities, or to support the development of remote laboratory activities during the pandemic. Speaking of the pandemic, with using textbooks, a lot of the current textbooks are starting to move in a way that differs a little bit from some of the traditional print textbooks. So here we have Chemistry, Life, the Universe, and Everything, more commonly known in the community as the CLUE textbook. This is by Cooper and Klimkowski. And what they've done is they've got a rather streamlined book that takes the perspective of many of the newer books, that there are some topics that just having a lot of text in a chapter doesn't help to explain well. And so they feel that those topics are best taught and experienced and understood through a lot of interactive activities. And to be frank, we couldn't agree more, and have built quite a bit of support for some of those. So I'd like to go through the topics that the CLUE textbook, this is the CLUE General Chemistry textbook, so this is targeted towards a introductory college level textbook, but the concepts are ones that you would see in an AP chemistry course or a standard high school chemistry course. So let's see. So they start off, as many of us do when we're teaching chemistry, with energy, frequency, and wavelength conversions. And we have calculators for that, where you can go from the energy or the frequency, and we have step-by-step support for that conversion along with the frequency and wavelength conversion using the appropriate calculators. When introducing electronic configurations, as you're introducing the periodic table and the orbitals that the electrons go in, we have support for electron configurations and short electron configurations. Right now, we don't have step-by-step support for this, but that will be coming over the next year, hopefully sooner than that. When teaching about valence electrons, it is often useful to have a pictorial representation using the so-called Aufbau diagrams or orbital diagrams, where we have each orbital represented as a square with arrows showing the electron count. We have step-by-step support for fully deriving these things and building them up. We also have support for the valence electrons, counting them, building it from the short electron configuration that one gets here, and then determining the valence electrons. For Lewis structures, usually the next topic after you've gotten comfortable with atoms, you now start stringing them together in structure, and we have full support for Lewis dot structures for both inorganic complexes like nitrogen dioxide, or more complicated organic species that you might get at the end of an introductory course or at the beginning of your organic chemistry course. Stoichiometry is central to all of chemistry courses and day-to-day laboratory activities for that matter. And we have, again, full support for this step-by-step. When you pass us information, in this case, we've been given how much of the starting reagent and how much of the product, so then we can, therefore, we can compute the theoretical yield and percent yield. And this all comes out in tabular form. The stoichiometry is currently undergoing an overhaul, so we hope to have a new and improved version of this in a year from now. But we still have current step-by-steps right now. After the introduction of stoichiometry, many courses introduce oxidation numbers in the context of redox reactions, and we have full support for determining oxidation states of a particular individual species. We also have support for returning the half reactions and the reductant and the oxidant. We don't yet have step-by-step support for that, but that's on the docket for this next year. As I said earlier, our kinetic support is brand new this year. And as I said, if you pass in an equation that can be balanced, as in this case with thionyl chloride and the sulfite anion, or over here we have the gaseous reaction of chlorine and fluorine, then we can build up the rate of reactions or the rate of conversion, and we have full step-by-step support for that, and are clear to point out what sort of assumptions were made along the line, again, in supporting our more advanced courses that they may be worried about such things, which gets shoved under the rug in the introductory courses. Our thermochemistry is on the docket for next year. We already support reaction thermodynamics for balanced chemical equations. We will be adding step-by-step support for this to show how to do the math in more detail than is currently given. And we also have added this year the heat transfer reaction for doing specific heat calculations that are also commonly introduced in the thermochemistry modules in various courses. Lastly, I'd like to point out the other new topic that we had, the equilibrium. Again, this is a topic that the CLU textbook views as well suited for just problem sets and teaching offline rather than having a big blurb in a textbook. And we now have support for equilibrium constants. And again, the logic is smart enough to figure out, in this case, here we have the dissociation of water, and it notices that and returns a KW appropriately and explains it all with the step-by-steps. And likewise, for our more advanced courses that are working with reaction quotients, we have that here. And again, the logic is smart enough to realize that we're in the concentration basis and appends the symbology accordingly. Lastly, I'd like to point out what we've been taking and working up with the Wolfram Alpha Notebook folks, is that we've been trying to take all these great step-by-step and Wolfram Alpha support and bring it over to the Wolfram Alpha notebooks, which I think is going to become the premier way of doing chemistry in the Wolfram area. So if you'll notice here, I have Wolfram Alpha notebook input cells, and so I'm just going to evaluate those. And so you can put, this is again the Wolfram Alpha notebook. What's cool is that you can just do conversational English here, and it understands what's going on. So you see, if the student, I need a periodic table, then what you'll get back is just that, a full periodic table. You have control to get, you can control the interpretation if it didn't quite understand your query, and you can immediately pop over the full Wolfram Alpha results if you want. But now this periodic table is right here ready for the student to utilize while they're solving their particular problem or activity. And what's nice about the Wolfram Alpha Notebook Edition compared to just Wolfram Alpha is that you can now say things quite colloquially as show me the structure of a particular molecule. In this case, dexamethasone. And what you get back is the structure diagram. And while that's helpful because the 2D representation of molecules is one way that we communicate structure, most of us need to think about things in 3D. And with Wolfram Alpha notebooks, you can immediately utilize the molecule 3D, plot 3D aspects, and just say display the molecule plot, stick plot, and space filling plot, and see the 3 different common representations of molecules. And they are fully interactable, they are rotatable, right live in your notebook for your students. So your students can both visualize in 2D and 3D side by side. They can rotate right there in their notebook in the problem that they're working on. And they can see how you can have conversations about the different representations and why one is useful in some cases and not in the others, and really dig deep into these basic chemistry concepts. You can also immediately get access to the step-by-step support for various things. So in this case, we had the orbital diagram that I pointed out earlier being a new feature this year, and you just show steps for whatever the concept is. In this case, what you get back are your sort of usual step-by-step steps, and you can just show all of them right away. And again, we see live that the student gets the plan of all the gory details of what to do to build up these sorts of problems. You get the data. We also have graphs and pictures to help explain the concept. So here's your standard Mandelung diagram, and the student then is walked through building up the orbital diagram. Lastly, I'll leave you with an example of our unit conversions, which we have step-by-step support for. So again, you just request step-by-step support, and sure enough, you can get all the steps for working through the problem, doing all the dimensional analysis, which is laid out in the traditional fraction forms, so that the student can follow along. And so I'm very excited to show you the Wolfram Alpha Notebook Edition. Like I said, I think it's going to be the preeminent way that chemistry is done and taught with in the Wolfram language system. And I'm hoping that you'll take time to check it out. Lastly, I will walk you through all these, but there are quite a bit of chemistry resources in the Wolfram universe, and I've tried to summarize these here for you. We have a wide variety of tutorials for getting yourself, your colleagues, and your students up to speed on our technology. Particularly helpful are the quick takes for interacting with Wolfram Alpha. Then I've summarized some of the education support. Again, links to the demonstrations for chemistry, our essays in the notebook archive, and some links to current literature that's come out in the last few years showing how our technology can be used in real life learning spaces in the chemistry environment. And then I've got links to the other support for our language, the Wolfram function repository, all these new functions by our team and other practicing chemists, along with links to other support. And with that, I'd like to thank you for your attention and answer any questions before we all head over to Jason's talk after this. Okay, so if you haven't been to a talk, I understand that if you have a question, you need to raise your hand so that I can then unmute you and we can chat. If not, I guess we can end here and move over to the other upcoming chemistry talk at 9:30.
Jason, there was a question in the chat on the Pathable site.
I see that. Thank you. So the question is, polymers do not appear in your talk. Are they not expected to be part of the subject at Wolfram Technologies? No, that's not true. We do have support for polymers in Wolfram Alpha. We have not done anything new with polymers at the moment, but there is some support for it, and I'd be interested in hearing what sort of support we can add in the future, or what would be useful in the classroom for teaching polymers. So that's where we are with that. I should just point out, if you are already using the Wolfram Alpha technology, the step-by-steps, or the molecule package in Wolfram, please don't be shy. Use the feedback forms to send suggestions that you might have either today or in the future. We're always looking for feedback, and would love to hear what you would like to see the tech do and new directions that it should be going in. Well, if there aren't any more questions, I'd like to thank you again for coming and encourage you to stick around to the next talk at 9:30 by my colleague Jason Biggs. He'll be explaining more details of the new features that are in the molecule package in the Wolfram language.